Hello everyone, I'm Zijian Cai, a PhD student in CEDA group in LBL and UC Berkeley. Welcome to join this virtual meeting. In this video, I'm going to present a new group of lithium-ion cathode materials that can achieve high power density and energy density at the same time. So first of all, I'm going to give a brief introduction on the lithium-ion cathode materials. We all know that the cathode materials has already been dominated by the layer materials, such as lithium cobalt oxide and NCM. Those layer materials has already been commercialized and performed pretty well. So why are we trying so hard to explore the new chemical space and structural space? What's the shortcoming of these layered materials? Well, it turns out that the cobalt is so critical for these layered materials to stabilize the structure, with larger and increasing demand of the lithium-ion battery in portable devices and electronic cars. Research has shown that the cobalt supply can barely satisfy this demand in the coming few years. Although cobalt is substituted by nickel and manganese in NCMs, the nickel is also expensive. So more earth-abundant elements are needed to substitute cobalt and make a cobalt-free and even nickel-free cathode materials. To do so, spinel is a very interesting and promising structure. Instead of cobalt, manganese is used in the spinel compound, which is much cheaper than cobalt. Here is a spinel structure. And you can see the 16D site is all occupied by the manganese, and they face share with the vacant tetrahedral site, which is the 8B site. And for the lithium, all the lithium sits in the 8A site, and they face share with a vacant octahedral site called 16C site. So lithium is migrating from one 8A site to another through this vacant octahedral site. And due to the low migration barrier and 3D migration network, the spinel structure is very favorable for lithium transport. However, this spinel structure cannot do fast charging. Even at low rate, it cannot deliver high capacity. So why is that? So let's take a look at the cycling curve and the free energy curve during cycling. You can see this, when you lithiate the lithium manganese spinel, instead of go through a solid solutions reaction, they actually go through a two-phase reaction. The insertion of the lithium will form a well-ordered tetragonal phase, where the lithium all sits in the octahedral site. And what makes it worse is the collective Young-Taylor distortion in the tetragonal phase. So in this phase, all the manganese are 3+, and it's a Young-Taylor ion. And the well-ordered structure will make the Young-Taylor behavior collective and elongate the C-axis. And the mismatch in the C-axis between these two phases creates a large strain at the phase boundary, and this will move through the particle during the cycling. And after a few cycles, the particle will crack and finally fail. So lithium manganese spinel can never practically cycle at 3 volts region due to this problem. In this work, we propose two strategies to suppress this two-phase reaction. First one is the lithium over stoichiometry. That means putting more lithium into the structure. And in this strategy, the cation will disorder because if you look at this formula, that's actually the transition state between spinel and disordered rock salt. Although this disordering will block some lithium percolation network like this lithium here, it will also break the collective Young-Taylor behavior and could even make it a solid solution reaction instead of a two-phase reaction. And second strategy is to apply lithium for manganese substitution, which enables more accessible lithium. As the desoldering in the first strategy blocks some lithium, the second strategy reconnected into the percolation network. This will also create a lithium-rich environment and make fluorination possible. And fluorination can lower the manganese valence and achieve more manganese redox. As a result, in the design compound, the cation to anion ratio is over 3 to 4 because of the lithium over stoichiometry. And lithium content is more than manganese content because of the lithium for manganese substitution. And following these two strategies, we have synthesized this compound by mechanical ball milling. Another sample with even more fluorination level was synthesized to further increase the manganese redox. And to characterize the structure, we did synchrotron XRD and neutron diffraction. The diffraction data showed both materials adapt to the spinel-like structure. Combining the refinement of the diffraction data, we can get the site occupancy in such spinel-like structure here. Recall that in order structure, all the manganese are in 16D site and leaving the 16C site vacant. However, in these two materials, part of the manganese is distributed in 16C site. That means around 30% of the manganese disordering. So we will call this kind of material a partially disordered spinel. After testing the electrochemical performance, we found both of them delivers very high capacity and energy density. And they were cycled under 50 milliampere per gram current density. For the first compound with lower fluorination level, the initial capacity is higher than 360 milliampere hour per gram. And the corresponding energy density is higher than 1100 watt hour per kilogram. And even if we cut the lower voltage limit at the 2 volts, it's around here, it still can deliver a capacity higher than 300 milliampere hour per gram, and the energy is higher than 1000 watt hour per kilogram. And for the compound with a higher fluorination level, the initial capacity and energy density decreases, but still it's pretty high comparing to typical cathode materials. Then if we take a carefully look at the voltage profile, we draw two vertical lines here to show the theoretical manganese redox contribution. Usually manganese cannot go higher than 4+, so there will be a line here. And we assume the cation to anion ratio is lower than 1, so there is another one here. And the capacity between these two vertical lines is a theoretical capacity. But when the compound is cycled between 1.5 to 4.8 volts, the actual capacity is twice the theoretical capacity, which is expected from the oxygen redox at high voltage region. The compound with more fluorination level provides more theoretical capacity. So the hysteresis is also smaller because of less oxygen redox contribution. But it delivers less capacity, which might be caused by the fluorine-induced short-range order, which makes the voltage profile more steep. And for both of them, there is no voltage plateau at the 3 volts region, which is observed in older spinel. As we proposed, this is because the cation disorder induced by the lithium over stoichiometry. And here shows the capacity retention of the two samples at different voltage window. When this sample is cycled at 1.5 to 4.8 volts, although the initial capacity is high, the capacity drops relatively fast. This is due to large amount of the oxygen redox contribution. But when cycled within a small voltage window, it can achieve a capacity larger than 200 milliampere hour per gram, and it's still pretty stable. And with more fluorination level, the capacity gets more stable even when charged to 4.8 volts. And this is because of the fluorine can make it rely less on the oxygen redox, and the fluorine can also suppress the irreversible oxygen loss. And to quantify the manganese valence at each state of charge upon cycle, we perform the soft S3 mRIXS on manganese L edge. This is a technique that pretty much similar to the soft ECS, but it can get rid of the edge distortion. So the quantification of the manganese valence is more accurate. By fitting the spectra with manganese 2+, 3+, and 4+ standards, we can get the valence of the manganese at each state of charge. I will show these results later, but before that, I'm going to show the characterization on another main and reversible contribution to the capacity from oxygen redox. And here is the oxygen Ki mRIXS, which is an advanced technique to characterize the oxidized oxygen. And this technique is more precise and it's a more direct evidence to the oxidized oxygen in the lattice if you compare to typical soft ECS spectra. And this 2D mapping of the oxygen K edge gives the intensity by color. Blue means low intensity and brown-white means high intensity. And from the literature, we know that this feature pointed by the red arrows is a characteristic feature for oxidized oxygen in the lattice. And we can see this feature does not exist in the pristine sample, but we can observe it when it's charged to 4.5 volts, indicating the oxygen redox start around this voltage. And the intensity keeps increasing when further charged to 4.8 volts, indicating more oxygen anions is oxidized. After that, during discharge process, the intensity of this feature gradually decreases, and you can still observe it with low intensity when discharged to 3.6 volts. But when you further discharge it, this feature will totally disappear. And this phenomenon indicates the oxidized oxygen get reduced to 2- during discharge, meaning a reversible oxygen redox process. Now, combining these two spectra that characterize both manganese and oxygen redox, we are able to draw this figure to show which redox contribute to each region of the charge and discharge process. And the blue curve is the manganese valence change. The manganese was oxidized first during charge and got a little bit reduced at the top of charge. This is mainly due to the irreversible oxygen loss happening on the surface on high voltage. And during discharge, the manganese valence keeps constant first, and then get reduced almost linearly with the lithium insertion. And from this results and previously mentioned the qualitative measurements of the oxygen redox, we use the gray color and the pink color to mark the contribution from manganese and oxygen redox respectively. And during charge, the manganese redox dominates first, and when the voltage goes higher, the oxygen redox starts to overlap with the manganese redox, shown by the gray-pink color here. And after using up all the manganese redox rather well, after using up all the manganese redox rather well, all oxygen redox dominates at the high voltage region. And during discharge, the oxygen gets reduced first, and the manganese valence remain constant. And then when the voltage gets lower, the manganese reduction starts to overlap with the oxygen redox. And at low voltage region, the manganese redox again dominates. After proving this partially disordered spinel structure can deliver high capacity at normal rate, we start to think about the high rate performance. Because we have already suppressed the kinetically slow two-phase reaction, and with this spinel structure, which is favorable for lithium transport, we should get the high rate capability from these two materials. And after measuring the voltage profile on the current density ranging from 100 milliampere per gram to 2000 milliampere per gram, you can see the capacity only drops around 30%. It means that this material is able to deliver around 250 milliampere hour per gram capacity on the current density of the 2000 milliampere per gram. Note that this means the material can can finish each charge and discharge process within 8 minutes. And this test was done with electrode composing 70% of the active material and 20% of carbon, 10% PTFE binder. And when we further push the rate of the charge, we increase the carbon content to 50%. So we can get rid of the electronic conductivity issue and get the intrinsic rate performance from the material. And we found even on the 20 ampere per gram current density, this material can still deliver a capacity over 100 milliampere hour per gram, which means the charge and discharge process can be finished within 30 seconds. And we also make this recon plot to compare our materials with other state-of-art lithium-ion cathodes, such as lithium excess DRX materials and layered materials like lithium cobalt oxide, NCM, and lithium-rich NCM. And this data are the highest rate performance we can find in the literature. It turns out that our material can achieve the highest energy density at the same current density. And this result is pretty remarkable, especially when we consider our material has partially disordered spinel structure and heavily using the oxygen redox, which are both regarded to be negative effect on the rate performance. So we believe that the disordered system is not limiting the rate performance, as long as we can carefully manage the cation distribution, like in this case, spinel-like order. And also, oxygen redox might not be the intrinsically slow process. But what is the intrinsically slow process? To characterize how the structure changes during the cycling, we perform axial synchrotron SRD measurements. From this data, we can refine the manganese occupancy to see whether and how the manganese can migrate. And here is the result. The manganese occupancy in 16D site and 16C site is quite stable during charge and discharge, although there is a small changes of the manganese valence occupancy at the bottom of the discharge. But it's not only small, but also reversible when it's go back to the second top charge. In other lithium-rich materials, oxygen redox almost always couple with the cation migration, which is slow. But in our materials, the manganese migration is so limited, even at the top of the charge, where the oxygen redox is heavily used. So this might be the reason that the high rate capability can coexist with the oxygen redox. And we believe the oxygen redox is not intrinsically slow, but the cation migration is. To summarize my report, here is the take-home message. In this work, we apply lithium and cation over stoichiometry to tune the cation ordering and form a partially disordered spinel structure. And this material can achieve high capacity and energy density using a larger amount of the reversible oxygen redox. And besides, we found this partially disordered spinel structure can deliver high rate capability. And we believe that the cation disorder and oxygen redox is not limiting the rate performance. And last, I want to thank Professor Gerben-Sieder for all the guidance and help on this project. And also thank to Huiwen Ji, who is the first author of this work. And thank to all the collaborators and founders. And thank you all for listening to this video. Thank you.